All right, everybody. So today we are going to be covering exponential functions and rational exponents. So let's go ahead and get started on our warm-up. Our warm-ups today are pretty much just going over exponent rules. I am going to write down the exponent rules on here. You should already know these. You learned them last year. People like to forget them though, so I am going to write some helpful hints down on here. So on this one, the helpful hint would probably be that, say you're looking at a to the x times a to the y, your result will be ax plus y. So that's one of your exponent rules. Whenever you're multiplying, you are going to add the exponents and keep the base. So the base up here with this a to the x, that base is a. Your exponent is x, base is a, exponent is y. So down here, you're looking at a base of 2, so we're going to keep that 2, and then we are going to add 3 and 5. So you're looking at 2 to the 8th. And that is writing this answer with the given base and a single exponent. All right. Oh, and this is also the pages out of your textbook. This is M389. M389. And this is in volume 2. Okay. If you do not have the textbook with you, just pause the video and write down warm-up number 1. 2 cubed times 2 to the 5th equals 2 to the 3 plus 5 equals 2 to the 8th. Okay, so if you need to pause the video to write these things down, you need to do that. For number 2, this is division. So whenever you're dividing these things, so your base is a again to the x power, base is a again to the y power, and your result will be that base a to the x minus y. So what we're doing here is we have a base of 2, and then we have 4 minus 8, which gives us 2 to the negative 4th. With negative powers, the other thing that you're looking at is a to the negative x. You're looking at 1 over a to the x power. So with negative powers, you kind of flip your fraction, which this is not a fraction yet, but we will end up making it a fraction, and it'll be 1 to the 2/4. All right. I'm going to have y'all do number 3 yourself and input your answer once you have it. So hopefully you did the same thing as last time. You have 5 and 5 minus 4, which is 5 to the 1st, which is just 5. But the answer that you should have put was 5 to the 1st because we were wanting it with a single exponent. Even though you can typically ignore an exponent of 1, but I wanted to make sure y'all got what that exponent was. All right, for number 4, again, y'all are going to answer this and then come back and check your answers. So again, this is multiplying, so we're going to add those exponents and keep our base. So we're looking at 4, 0 plus 1, which is 4 to the 1st, which is actually just 4. All right. So now we're going to get into characteristics of exponential growth. This is activity 1.1. We skipped the getting started in the textbook, so now we are on page M392. Is where this is. This is the top of M392. So we're going to consider another scenario that can have integers or fractional intervals in a laboratory experiment or a certain bacteria doubles each hour. Okay, so we're going to suppose that the bacteria population starts with 1 bacterium. So that means that at 0 hours, there is 1 bacterium. Because you have to start somewhere. So if we're going from 0 hours to 1 hour, and it doubles each hour, we are going from 1 plus 1, which will give us 2. To get to the second hour, we'll do 2 plus 2, which gives you 4. 4 doubled is 8, and 8 doubled is 16. So let's go ahead and click over to the next question. So 2, 4, 8, 16, we filled in our table correctly. So we are going to, pretty much what we're just going to do here is determine the exponential function that represents the growth of the bacteria. So there's a couple ways that you could go about this. And one way that you can go about it is, so we're constantly doubling by 2. So we're doing 2 to the x power is what this is, because it's an exponential. Because 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and 2 to the fourth power is 16. I know that because I know my exponent rules, but let's say that that was something that you were struggling with. You could come over here to Stat, click Edit, and do the exact same thing that we did for the quadratic regressions, except this was 1, 2, 3, 4. And this was 2, 4, 6, 8. Oh, not 2, 4, 6, 8. 2, 4, 8, 16. Click Stat, go over, and look for exponential. So see, there's a lot on here. The one that I think may be exponential is that 0 right there. So let's click 0. Click enter, 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 enter. Calculate. So yes. So what we're really looking at here is f of x equals 1 times 2 to the x power. So that does give us f of x equals 2 to the x power here. So now we're going to graph our exponential functions to show the bacteria growth over time on the coordinate plane. It's located at the end of y'all's lesson. So it is on, this graph is on page M3104. I just drew a little sketch down here on my number 2 in the textbook. So either which way you want to go about it. But let's come over here, and of course I'm going to zoom in because we all know how fun my graphs are. We were looking at 1, 2. So these may be a little bit hard to graph on here, even with me zooming in. Then we are looking at 2, 4. I believe that's 2, 4. Forgive me if it's not. 3, 8. Hang on, we're just going to draw a line on 3 and keep going up to we're at 8. I believe that right there should be 8. Again, forgive me if it's not. 16. Oh, I can put a ruler up here. Let's do that. I want it to turn though. Oh, there we go. Okay. Straight line, and we are looking at 4. And we are trying to find 16, so we're going to have to go up some. And 16 is this line right here, so that will be our point right here. So, and like I said, if you're off by like a dot or something like that, it's not that big of a deal. And hopefully you remember from earlier that we were talking about our first point that was at 0, 1. So let's also plot that point on here. So 0, 1. And then kind of connect the dots. So this kind of looks like half of a parabola would kind of be a way to look at it. The exponentials, they kind of do half of a U shape for their graph. So that's how you can recognize it. So say you were looking at this table and I asked you to write me an equation and you had no idea what to do. So I would draw a little graph over there on the side and see what it looks like. Because hopefully you remember all of our absolute value graphs, those always looked like a V. Our quadratic graphs always looked like a U. And then hopefully you'll know all your linear graphs look like some lines. Okay. Nice little review. All right, so now we are actually going to start talking about the square root and the constant ratio of an exponential function. I deleted some of the slides. So this is actually on page, let's get the whole page. So actually a whole 2 pages. This is actually on page M395. So a rational exponent can be written in radical form using the definition. So we're looking at a to the power of 1 over n. And you can rewrite that as n to the square root of a. So say it was a, oh, and when the index is 2, the index is that n right there. So when the index is 2, it's usually just the square root. So an example of what you're looking at here, so say we were looking at a to the 1/3, you'd be looking at the cube root of a. So you're writing of whatever root the number is in the denominator of your fraction of that base. And the base here is a, the base here is a, okay? So you're not going to want to lose that. All right, so here is even a worked example of it. So we're going to consider the properties of exponents to rewrite expressions in equivalent forms. So, and this even shows you how in the last example, we were looking at 1 divided by n for our exponent. Here it's a number divided by a number. So it's an actual full fraction here. So whenever it gives you a full fraction like that, there's kind of 2 different ways you can go about it. So you can separate the numerator from the denominator. So over here on the left side, they kept the fraction with the base and brought the numerator outside. On the right, they brought the numerator, or they left the numerator with the base and brought the fraction outside. I hope I said that right. If not, you knew what I meant. So they kind of went about it 2 different ways. So on the left side, that 2 to the 1/2 power is the square root of 2. The 2 there is implied. That's what we talk about in class because there's a 2 right there. That's why we have to have a pair of something to pull out, if y'all remember. And then we looked that it's cubed, so we have 3 of them. And as y'all remember, we could write this all under one big giant square root. And you would pull out one set of 2's and you'd be left with 2 square root of 2. The other way that they went about it, and this is the way that I would probably go about it, is that they were looking at 2 cubed under the square root. So they wrote their 3 2's, pulled that 1 2 out, and were left with 2 square root of 2. So there's kind of 2 ways you can go about it. I will probably be doing that first or that second way, just because personally that makes more sense to me. If you like the first way that they did, oh shoot, I think I said I like the first way. I'm going to be doing it this way. If you like this way, go for it. Okay. It's early in the morning. I haven't had my coffee yet. All right. So here's another worked example, and it's another way that you can go about writing it. And it's just they're using the product rule here. Does it say what rule we used it back here? No, but this is showing you with the product rule. So what they did here was we're still looking at 2 to the 3/2 power. They separated that fraction out into 3 1/2s. Because if you were to add 1/2 plus 1/2 plus 1/2, you would get 3/2. So then they wrote it 3 times, wrote the square root 3 times, and then had it under that radical form, and if you were doing this, you should keep simplifying to get to square root of 2 here because you recognize you can pull 2 of those out. So here on 5B, very similar example again. So you recognize that you can write 2 squared as 2 times 2. You can circle that, and you recognize that you can pull 1, 2 out. All right, so now we're on activity 1.3, the cube root constant ratio of an exponent function. So pretty much what they're talking about here is that, so in the previous activity, we looked at the exponential function fx equals 2 to the x power. When we were talking about x was equal to 1, so our input interval was 1. Then we changed our input interval to 1/2, and that was where we got the square root of 2. So down here, if we change it to 1/3, you're going to be looking at the cube root of 2. The reason for that is because remember, that's the n down here, the 3, and that number n goes with your square root. Well, it's not a square root now, it's a cube root. It's your root. So now we're going to look at a constant multiplier where the input interval is, let's move this image, see what that says. According to my paper, it says 1/3. So as you can see down here on the table, so not zooming that much. But as you can see on the table, so when x is 0, it's 2 to the 0 power. So here's you're going to be looking at 2 to the 1/3 power. And I'm going to have you input what you think the next two are going to be and then come back and check them. So you're looking at 2 to the 2/3 here and 2 to the 4/3 here. So again, we're going to be doing the same thing that we did last time, changing 2 with a fractional exponent into a radical of some type. So with this first one here, remember whatever number is on the bottom is going to be what goes with the root. So this will be the cube root of 2 to the first power. Now, the first power you can just kind of ignore because it's understood to be there. Let's do this in a different color so y'all can see it probably. So again, the n is on the bottom of your fraction. So again, we're still looking at a 3. So we're still looking at a cube root of 2 because 2 is our base. 2 is our base this entire problem. And then the difference here, though, is that cube root of 2 is then squared. So where we looked at this earlier was on, it was some worked examples up here. Okay, so here. So there was 2 ways that we could go about writing it. So you can either write 2 cubed or the square root of 2 cubed. So another way that we could come down here and write it would be, so a way that we could write this final one was we could also look at this as 2 to the 4th cubed as well. Okay, so you can go about writing it 2 different ways. Again, this, whatever number's on the top is going to be an exponent somewhere in your problem. Whatever number is on the bottom is always going to be with your root. And I always like to call them square roots even though they're cube roots here because we're talking about the cube. So now we're looking at activity 1.4, and this is on page M398. Okay, if you're keeping up within the book. If not, like I said earlier, if it's something you need to write down, you need to pause it and write these notes down. These are your notes. So in this lesson, you have been writing powers with rational exponents. You have shown that you can rewrite a rational exponent in radical form. So the rational exponent is a to the power of 1 divided by n. Then the radical form is n to the root of a, okay? So that is what that means, a bunch of big words. So now we are going to rewrite some of these together. So like I said earlier, you have your base every problem. So our base here is that 7 because it's under our square root. So we're looking at 7, and then whatever power that 7 is to, which is 1, is going to be on the top of your fraction. And whatever number is with your root is the number on the bottom of your fraction. So this will be 7 to the 1/3 power. So let's look at 19. So here we're looking at the 5th root of x. So if anybody can take a guess, what's your base here? It's that x, and it's to the, what power is x raised to? There's not one shown, so it's 1. And the number that is stuck with the root is 5. So it's x to the 1/5. I'm going to have y'all do this one. And remember, if there's not a number with that root, it is understood to be a square root. So it should be a 2. So hopefully you got that this was y to the 1/2. Because y is to the first power, and the square root is understood to have a 2 there. So now we're going to rewrite the expression in radical form. So we're now going to take this 8 to the 1/4 power and write it with a root. So our 8 is to the first power, and it is to the 4th root because that 4 is in the denominator, so it's going to go with that square root. You don't have to have the 1 in there. Just if that makes you happy, you can do it. All right, I'm going to have y'all do number 2B. All right, hopefully y'all got that this was to the 5th root of z to the first power. or just the fifth root of z. I'm going to have y'all do this one as well. Hopefully you got this as the cube root of m. So we're going to use the properties of exponents to rewrite a to the m divided by n in radical form. So what we're looking at here is a to the m to the n. And so the ways that we can go about rewriting this, and this is the way that I like to go about writing this, is a to the m to the 1 divided by n. So that n is what's with our root, our a is our base, and our m is to that a. So the other way that they could also go about writing it, if you liked the other way, was that we did a to the 1n to the m. So you're looking at n to this root of a to the m power. So you can go either way. I like that first way better. This is the one that I prefer to write. I originally was writing it like this, but I like that top way better. So you can go about writing whichever way you want. Both of those answers are correct. One I just think looks prettier. All right, so number 4. So we're now on page M399. So again, I will probably do the first two for you, and then I'm going to have y'all do the last two. And if y'all have any questions over any of this, join my live Zoom link the last 15 minutes of class. And if you have any questions or need me to clarify anything, then would be a very good opportunity, or email me and we can set up a time. So our base here is 4, so I'm going to draw a root to the 4. The number that would be right here is 2, so that's making this a square root, so we really don't need it. And the number that's going to be the exponent here will be that 3. So we're looking at 4 cubed underneath the square root. Or if you liked writing it the other way, you're looking at 4 cubed like that. You will get the same answer. And the reason that you're going to get the same answer again is because you're looking at 4 times 4 times 4 here. Pull out a 4, you're left with a 4. Over here, you're looking at the square root of 4, square root of 4, square root of 4. And again, you can write all those underneath 1. So again, pull out 1, left with 1. So they end up being the same thing. It's just how you like to go about looking at it. I like looking at it the first way. If we're rewriting B, so we're looking at 5 cubed, because 5 and the number on the top, and that is to the 4th root here, because that 4 is in the denominator. All right, let's look at 4C. So this has an X as your base. That's the only thing that's different here, but I'm going to give you all an opportunity to figure out which one this is. So what I got here is x to the 4th to the 5th root. If you have any questions about that, that 3 is on the top, so it goes with the 5. The 4 is on the bottom, so it goes with the root. On D, you're looking at y squared underneath a cubed root. All right. So now we're going to rewrite each expression as a power with a rational exponent. So you're going to be writing this, your base. So here we'll be writing 2 with a fractional exponent. That's what that means by rational exponent. So the number that is the exponent in this problem is that 3. So that 3 is going to be on top, and the number that's with our root is that 4. So that's how you're going to go about rewriting these. So, and if I would have written this problem out, it would have been 4 to the square root 2 cubed. So again, that cubes that exponent, so it's going to go on the top, and the 4 is with the root, so that goes on the bottom. All right, so here we are looking at our base of 5. This is under a square root, so there will be a 2 on the bottom, and it is to the 4th power. So we can actually even simplify this fraction right here. So what we're really looking at is 5 squared. All right, for C, I'm going to have y'all input your answer real fast. Remember, exponent on top, number with the radical on the bottom. So you're looking at 8/5, I believe. X to the 8/5. All right, number 5, again, remember exponent on top, number with the radical on the bottom. So what you're looking at is y to the 10th fifths. And again, we can even simplify this even more, so this will end up being y to the 2nd. All right, so this is a way that you can rewrite the numerical expressions in radical form using the rule of exponents. So remember, whenever you are multiplying numbers like this, you pretty much just add, and you can go about rewriting it this way. This kind of gets very complicated very fast. Pretty much what you're going to want to do is just follow rules that you recognize and go with that. So we're about to work out a couple example problems here. You can go about it like this if you like going about it like this. I am going to show you another way though. And then again, here is another one. The way that we're going to go about it is this way right here. If you love some exponent rules, you can go about it like this, but I'm going to go about them like this, okay? So like, for example, we're wanting to rewrite the expressions, extracting the perfect squares. So pretty much we're just wanting to simplify non-perfect square roots here. So y'all know my favorite little thing to do when it's not a perfect square is make a factor tree. So if I made a factor tree here, I would have 2 and 25 and 5 and 5. I would circle my ends of my factor tree as I go down. So you'll have 5 times 2. Circle of 5, pull out a 5, square root of 2 would be your final answer here. I've recently learned another way to do these. So if you're kind of struggling with the factor trees or your numbers get lost, another way that you can go about this is, so you write 50. You draw kind of like a backwards L, so down and then underneath. And you want to either see if you can divide by a 2 or a 3. So here you can divide by a 2. When you divide by 2, you get a 25 left. And so you're going to put the 2 on the left and the 25 on the bottom. And then you're going to kind of do that backwards L again. And can 25 be divided by 2 or 3? No. So we got to kind of think a little bit bigger. Can it be divided by 4? No. Could it be divided by 5 though? Yes. So when you divide it by 5, you're left with 5. And so we got to think about 5. Is it divisible by 2, 3? No. That is divisible by 5 again, and you end up with a 1 on the bottom. So once you achieve the 1 down here on the bottom, you know to stop. All of your factors are then given to you over here on the left. So 2 times 5 times 5, which we showed over here earlier. So at that point, you can look at this, recognize that you're going to have 2 5s, pull that 5 out, and put your 2 under the square root. So if you're struggling with your factor trees, that's another way that you can go about it. All right, so let's look at B. So we're looking at 24. I'm going to do that new. It's called a ladder. This right here is called a ladder. I'm going to do that on the rest of these problems so that y'all can just kind of see a new way of doing it, because I know a lot of people are struggling with those factor trees. So we're looking at 24. 24 is, and so the reason you're wanting to do 2 and 3 first is because you're wanting to find the smallest prime number that's divisible by it that's not 1. So, and 2 and 3 typically are divisible at some point by that number. So this is divisible by 2. You'll be left with 12. 12 is, again, divisible by 2. You're left with 6. 6 is divisible by 2. You're left with 3. 3 is not divisible by 2, but it is divisible by 3, and you'll be left with the 1. So once you get to that 1 down here at the bottom, all of your factors are over here. I'm okay with at this point you recognizing that you have 2 2's and writing this as 2 square root of 2 times 3, which is 2 square root of 6. Now, like I said earlier, if you're really loving those exponent rules, you can go about it like that, but I truly just think that's going to make it a little bit harder on y'all in the end. So I would continue to go with finding your factors here. So on this C, you're looking at 3 square root of 20. You already have a 3 outside on the front, but you can still keep going with that 20. So let's come over here, do 20. 20 is divisible by 2, you're left with 10. Divisible by 2, you're left with 5. 5 is not divisible by 2 or 3, but it is divisible by 5, and you have your 1 down here. So again, your factors over here. You can pull out a 2, so you're looking at 3 times 2, square root of 5. If you are struggling with these, please join my Zoom call for the last 15 minutes of class, and I will help you out. I'm going through these kind of fast because we've already done non-perfect square roots. So this would end up being 6 the square root of 5. Okay, so this is one of those where it's those two radicals, but as y'all remember, whenever you're looking at two radicals, you can do it as 3 times 6 under one radical because they are both square roots. So 3 is in its purest form, but 6 we can divide by 2, and you're left with 3, which is 3. So you're looking at 2 and 3 here. Now, there's nothing that we can pull out, but again, we can rewrite this square root as 3 times 2. You can pull out a set of 3's square root of 2. And if you're questioning to see if those answers are correct, what you can do is click on your calculator. And while everybody's at home distance learning, you can download an app on your phone. I believe it's TI-84 or TI-83, and it's the exact same calculator on your phone. Okay? But if you are questioning if these are right, so we just did, let's get out of here. Let's make this a little bigger so y'all can see what buttons I'm clicking. So we just did the square root of 3 times the square root of 6. Now this is going to give you a decimal because that's not a perfect square. But if you were to do 3 square root of 2, you should get the exact same decimal, which you do. So you can check your answers for these. So on your quiz, nobody should get these wrong, should they? All right, so let's look at the next one. So we're looking at 3 times the square root of 12. So you're looking at the square root of 3 times 12. Again, 3 is already in its purest form. Let's do it with 12. 2, 6, 2, 3, 3, 1. So those are your factors. So let's rewrite this out. So 3 times 3 times 2 times 2. You can pull out a set of 3's and you can pull out a set of 2's. 3 times 2, which is 6. And that's your final answer there. So sometimes you'll have a radical or square root times the square root, and you will get a whole number. Because 3 times 12 is actually even the square root of 36. So you can check it like that too. All right. F. We're looking at 8 and 12. Okay, so this is one. What I would do here is I would probably take the square root of 8 times the square root of 12. And I would do 8 times 12 because neither of those numbers are in their purest form. So you're looking at the square root of 96. So I would then come over here and write 96, draw my little backwards L. 96 is divisible by 2, which gives you 48. 48 is divisible by 2, which gives you 24. 24 again, divisible by 2 gives you 12. 2 gives you 6. 2 gives you 3. 3 gives you 1. So this is a very good example where you are going to have a lot of 2's, and you're not going to be all confused because they're all here on the side. So at this point, again, just start circling your pairs. So you're going to pull out 2 2's and be left with 2 times 3. So you'll have 4 square root of 6. Okay? Again, we are going to, I believe we're going to skip a couple pages. So turn the page until this is on M3102. So we're skipping a couple pages here. And what we are looking at here is a way to simplify crazy expressions. So you're looking at the cube root times the square root of x divided by the sixth root of x. So what they did here was they put those square roots, cube roots, and sixth roots all in the fractional exponents. They then used their exponent rules to add on the top. They used their exponent rules of division to then subtract 5/6 from 1/6, and they got 4/6. They then simplified that fraction, and they got their final answer of the cube root of x squared. So the cube root of x squared is equal to the cube root of x times the square root of x divided by the sixth root of x. So we're going to work a couple of these out together. Okay, so there's like several different ways that you could go about this. Some I think are easier than others. I'm kind of going to go on this first one. I'm going to do how they were originally writing them just because it makes a little bit more sense to me. So the way that they were originally writing these, so this was going to be the square root of 3 because of that 2 to the third power. This was then going to be again taken to the third power because of that right there. And because of exponent rules, a power to a power, you multiply. So you're really looking at the cube root of 3 times 3, which is 9. The way that I would look at this is whenever we're doing square roots, you can write this 9 times. So I then like to look at this as 3 to the 9th. So let's write that out 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Barely fit on there. So let's start circling some pairs. So we'll be left with the cube or the square root of 3. But 3 times 3 times 3. So 3 to the 4th, pretty much. So 3 times 3 times 3 times 3 gives you 81. So we're looking at 81 square root of 3 is that final answer there. So pretty much what you're having to do is just manipulate these equations to where you can get your answer. The other way that you could go about writing this, I'll do it up here in purple, was that we were looking at the square root of 3 cubed, and then that was cubed again. So what you're looking at there is 3 cubed times 3 cubed times 3 cubed. So 3 cubed times 3 cubed times 3 cubed. So 3, 6, 9, it's exactly what we wrote out down here. Whenever you're multiplying, you add, so you were going to have 9 3s. So like I said, there's two kind of ways you can go about this. Some of them are easier to see, some of them are a little bit harder. Now, on this problem, I would use exponent rules, and I'm going to show you how to do it. So whenever you're multiplying, when you're multiplying just regular numbers, so like, for example, 2 times 3 here, just do 2 times 3. You're going to get 6. Whenever you're multiplying x to the 1/2 times x to the 1/2, remember when you multiply, you add exponents. So you're looking at x here because 1/2 plus 1/2 is just x. Y, you're looking at 1/3 times y to the first. 1/3 plus 1 is y to the 4/3. Now, at this point, you can still keep going because what you're looking at here is 6x to the cube root of y to the 4th. Cube root of y to the 4th is y times y times y times y. And you're looking at a cube root here. So you have to have 3 things to be able to pull one out. So you're looking at y cube root of y. So 6x y times the cube root of y, because you still have one y left under there. Because with our square roots, we have to have 2 things to pull out because the square is 2. If we're looking at a cube root, a cube is 3, so you have to have 3 things to be able to pull out. Okay. One more. Okay. Remember I said earlier, anything to the 0 power, literally anything to the 0 power will always equal 0 or equal 1, sorry. So this whole big thing right here is 1. That is your final answer there. So if on your test I give you something absolutely crazy, look at the power. If it's 0, your answer is just 1. So I do not have any physical paper homework for this. Your homework is going to be on Delta Math. Majority of you are not in my Delta Math class. I'm going to put the code, my classroom code, on the plan book for today's date, and you will have it on there. If you log in and you go to my class and you get in there and you still cannot find it, join my live Zoom call at the end of the class. If you're not in my Delta Math, would probably just be the best idea. And we will get you in there, okay? We will have one more day of notes, which will be on, let's look at my calendar. So this will be on December 9th and December 10th. A is 9th, B is 10th. You'll have one more day of notes, which will be on December 11th for A Day and December 14th for B Day. On December 15th and 16th, you will have a short little 10-question quiz. And on December 15th, 16th, 17th, and 18th in my class, other than taking this quiz, you will need to be working on makeup work. If you do not have any makeup work, I'll have a few activities on there, probably on Delta Math, that you can work on. But if you have zeros in my class, you need to go back to, let's all go look together. Let's go to the plan book. Oh, yes, I do. You're going to want to go in the plan book. You're going to want to go to last week. So you're going to want to click the arrows at the top to last week and come and click on this grades for quarter 2. I may even just post it on those makeup work days as well. But if you're missing a homework assignment, you need to come here and look at this PDF. It has the list of all grades for quarter 2. And when I posted this, some of these grades haven't even been taken yet. For example, your test and this quiz that you're going to be taking. But say you're missing classifying, adding, and subtracting polynomials homework, and you're going to know that by checking your Skyward. Go click back on the plan book and go all the way back to September 21st. You click the arrows at the top and it'll take you there. If you are missing a test for me, you have to email me to get a link to take that test late. If you're missing a quiz, you need to email me so I unlock the quiz and so I know to check your grade once you've done it. And then for Mathia, you just have to finish Module 3. I didn't end up assigning any more Mathia. Okay? If y'all have any questions, though, y'all need to reach out to me because this is the end of the quarter. Your semester grade is determining whether you're going to have to retake this class or not. So if you're passing, you're good. If you're failing, you will have to retake this class. So let's do the best we can to get those grades up so that nobody has to retake this class. That'd be awesome, wouldn't it? Like I said, though, if you have any questions, you need to join my live Zoom call that's at the end of class or email me or message me on Remind, okay?